The only photographs ever taken from the surface of Venus show something nobody expected. And before we dive into what those images revealed, make sure to get ready and hit that like button. Because this story gets stranger the deeper we go. In the mid-20th century, scientists thought Venus was a tropical paradise hidden beneath thick clouds, a humid swamp world that might harbor life. But when Soviet probes finally reached the surface, they found the exact opposite of paradise. They found hell itself, and what came back in those images has left scientists puzzled for decades. Venus is Earth's closest planetary neighbor, similar in size and composition, which is why astronomers once called it Earth's twin, but that nickname couldn't be more misleading. Now, the surface temperature on Venus reaches approximately 475 degrees Celsius, hot enough to melt lead, zinc, and tin on contact. The atmospheric pressure at the surface equals 90 times that of Earth, which is the equivalent of being 1 kilometer underwater in our oceans. The atmosphere consists of 95% carbon dioxide, creating a runaway greenhouse effect that turned Venus into the hottest planet in our solar system, even hotter than Mercury, despite being much farther from the Sun. This wasn't always known, and discovering these facts required sending machines into conditions so extreme that they weren't expected to survive, and most of them didn't. The Soviet Venera program began in the early 1960s with a simple goal: reach Venus and see what was there. The first attempts failed spectacularly because engineers were working with completely wrong assumptions about the planet. In 1967, the prevailing scientific model suggested Venus had surface pressure roughly 20 times that of Earth, which seemed high but manageable with reinforced aluminum construction. Venera 4 was built to these specifications, entering the atmosphere with confidence, deploying its parachute for a slow, controlled descent, but it never reached the ground. The probe stopped transmitting at an altitude of about 27 kilometers, and it didn't burn up from heat. It was physically crushed by atmospheric pressure that far exceeded its design limits. The probe was nowhere near the surface when the immense pressure collapsed its structure like a tin can in a hydraulic press. This catastrophic failure revealed the true scale of the problem facing Soviet engineers. The pressure wasn't 20 atmospheres, it was closer to 90, and suddenly, the entire mission architecture had to be reconsidered. Venera 5 and Venera 6 attempted a different approach by reducing parachute size to increase descent speed, hoping the probes would reach the surface before being destroyed, but both imploded roughly 11 kilometers above the ground. The engineers realized they weren't building spacecraft anymore. They were building submarines designed to dive into an ocean of supercritical carbon dioxide. Venera 7 represented a complete redesign, featuring a forged titanium sphere capable of withstanding 180 atmospheres of pressure, double the expected surface load. To achieve this strength, almost all scientific instruments were removed to save weight for armor. Windows were eliminated and solar panels were replaced with heavy internal batteries. The probe launched in August 1970, and during descent, the parachute reefing cords melted, causing parachute failure. Venera 7 didn't float gently to the surface. It fell like a brick, impacting at roughly 17 meters per second. Mission Control watched the telemetry stream flatline immediately and marked the mission as another failure. But during a routine post-mission review of the raw radio tapes, an astronomer noticed something unusual in the static. The probe hadn't died, it had toppled over on its side, pointing its antenna away from Earth, but it was still transmitting. By carefully processing the noise, and they recovered 23 minutes of temperature data from the surface, making Venera 7 the first human-made machine to successfully transmit data from the surface of another planet. Surviving the pressure was only half the battle because the temperature presented an equally deadly challenge. Standard silicon electronics fail instantly at 475 degrees Celsius, and traditional cooling systems don't work when the outside air is hundreds of degrees hotter than the machinery you're trying to protect. The solution was ingeniously simple yet brutally temporary. Turn the lander into a thermal battery. Before separating from the orbiter, engineers circulated supercooled fluid through the pressure vessel, bringing the internal temperature down to negative 10 degrees Celsius. The probe essentially began its mission as a block of ice falling into a furnace, and to handle heat absorption during descent, the interior was packed with lithium nitrate trihydrate, a phase-change material with a melting point of 30 degrees Celsius. When this substance melts, it absorbs massive amounts of energy without rising in temperature. So as Venusian heat penetrated the titanium shell, it went into melting the lithium nitrate rather than frying the electronics. This bought the lander roughly 50 to 60 minutes of operational time before the system boiled over and failed. The camera technology itself required complete reinvention because traditional television cameras from the 1970s used cathode ray tubes with large glass lenses that would shatter under external pressure. And putting a large glass window in the pressure vessel would create a structural weakness that could cause immediate implosion. Instead of a camera, Soviet engineers built a telephotometer, a mechanical scanner rather than a lens-based imaging system. The device remained safely inside the cooled titanium sphere, looking out through a tiny cylindrical quartz window thick enough to withstand the pressure. A small mirror rotated behind the window, collecting light from a single point on the surface and directing it into a sensor that measured brightness. The mirror moved slightly to measure the next point, and the probe transmitted this data as a stream of numbers rather than a video signal. Earthbound computers reconstructed the image line by line over many minutes, meaning if the probe overheated before the scan finished, the image would cut off mid-transmission. On October 22, 1975, Venera 9 survived the descent and transmitted data for approximately 53 minutes. It landed on a steep slope of roughly 20 degrees, and engineers had prepared for the worst-case scenario regarding visibility by equipping the lander with powerful halogen floodlights, assuming the thick clouds would block all sunlight and plunge the surface into deep twilight or total darkness. When the lens cover popped off, the sensors detected immediate strong illumination. The floodlights were completely unnecessary. The surface of Venus was not dark at all. Ambient light levels were comparable to a cloudy summer day in Moscow. The thick atmosphere scattered sunlight evenly, creating a soft, diffuse glow that eliminated harsh shadows, but provided plenty of light for photography. The camera began its 30-minute scan, and as data arrived on Earth, scientists saw something that contradicted years of theoretical predictions. They expected a sandy desert landscape worn smooth by erosion, because the dense atmosphere should create powerful winds that would scour rocks down to pebbles over geological time, but the image showed the opposite. The ground was covered in sharp, angular rocks with jagged, broken edges, implying the surface was geologically young and proving that wind speed at the surface was negligible. The atmosphere was calm. The image also revealed remarkable clarity in the air with no fog or dust near the ground, and the horizon was clearly visible in the corners of the panoramic frame. 3 days later, Venera 10 landed over 2,000 kilometers away and operated for 65 minutes, touching down on a much older, smoother plain with flat slabs of rock resembling dried magma flows. The difference between the two landing sites proved Venus was not a uniform wasteland. It had distinct geological regions with mountains, slopes, and plains. These black and white images were the first direct look at another planet's surface, but they couldn't reveal the true chemical nature of the world. In March 1982, the Soviet Union launched Venera 13 and Venera 14, representing the apex of the program. These probes were heavier, smarter, and carried more instruments than predecessors, with the primary goal no longer just proving the surface existed, but characterizing it chemically and visually. The telephotometers were upgraded to capture color by taking multiple scans using red, green, and blue filters, with data recombined on Earth to create composite color images. Venera 13 landed on March 1st, 1982, and survived for a record-breaking 127 minutes. The color images it transmitted were startling because the black and white images from 1975 had shown a stark, rocky world, but the color images revealed a landscape bathed in a suffocating deep orange glow. Everything was orange. The rocks were orange, the sky was orange, the horizon was orange, and this wasn't a camera malfunction. The atmosphere of Venus is so thick that it acts as a massive filter, absorbing blue and green wavelengths of sunlight as they pass through the clouds, allowing only red and orange wavelengths to reach the surface. To verify this, the lander carried a color calibration chart within the camera's field of view, containing strips of white, red, green, and blue paint. In the transmitted image, the white strip appeared orange and the blue strip appeared almost black, proving that a human standing on Venus would see the world in sepia tone with no ability to color correct the scene because there's no white light reference available. Venera 13 also broke new ground by capturing the first sounds ever recorded on another planet using a microphone designed to detect seismic activity and atmospheric discharges. The recording revealed two distinct types of noise. The first was wind moving at roughly half a meter per second, which is barely a breeze on Earth. But on Venus, where air is 60 times denser than Earth's atmosphere, this wind pushes with significant force. The microphone picked up a low, constant aerodynamic drone as thick air flowed over the lander's structure. The second sound was mechanical. The probe successfully deployed a pneumatic drill to collect a soil sample, and the microphone captured the sharp, explosive sound of the pyrotechnic charge firing the drill mechanism, followed by grinding noise of the bit cutting into basaltic rock, confirming that the dense atmosphere was an excellent conductor of sound. Venera 14 landed 4 days later on March 5, 1982, roughly 1,000 kilometers away, in a flatter, smoother region resembling cracked pavement of basaltic rock. The lander carried a spring-loaded arm designed to swing out and strike the ground with known force, allowing scientists to determine physical density and compressibility of the Venusian surface by measuring how far the arm penetrated the soil. The landing sequence was automated, first securing footing, then beginning camera operations after titanium lens caps were ejected by pyrotechnic charges. On Venera 14, the lens cap ejected exactly as planned, but didn't roll away. It landed directly on the spot where the compressibility arm was programmed to strike. Moments later, the arm deployed and hammered the object beneath it, and telemetry sent back to Earth indicated the surface of Venus was incredibly hard and rigid with zero compressibility. This was technically accurate data. The probe was measuring the titanium lens cap it had brought from Earth, not the actual Venusian soil lying centimeters away untouched. The camera confirmed the failure by transmitting an image clearly showing the arm pressing down on the center of the discarded lens cap, creating the most famous mechanical failure in the program's history. The mission data sat in archives for 30 years, while scientific consensus remained that Venus was completely sterile, with surface temperature and pressure making organic chemistry impossible. In 2012, however, Leonid Ksanfomality, a respected contributor to the original Soviet space program, published a paper challenging this view by re-examining raw panoramic sequences from Venera 13 using modern digital image processing techniques. His analysis focused on the timeline of images, and since the telephotometers scanned the scene repeatedly over the probe's life rather than taking single snapshots, Ksanfomality looked for changes between sequential frames and found them. He identified several objects that appeared to behave erratically, with the most prominent anomaly named the Scorpion. In early scans, the soil appeared empty, but in a scan taken 7 minutes after landing, a structured object approximately 15 centimeters long appeared with what seemed like a central body and curved tail. In subsequent scans, the object was gone. Ksanfomality argued the object emerged from soil, remained visible briefly, then moved out of frame, also identifying an object called the black flap that appeared to change shape and position. He suggested these objects emerged, fluctuated, and disappeared, proposing that inhabitants of Venus might utilize exotic chemistry rather than carbon and water. The global scientific community rejected these conclusions, with NASA scientists and Russian experts providing mechanical explanations for the anomalies. They argued the Scorpion and flap were likely pieces of the lander itself, as the probe was wrapped in layers of insulation and plastic that would melt, peel, and fall off as internal temperature rose. The movement wasn't biological. It was the result of the lander disintegrating under thermal stress, with shifting shadows caused by changing sun angle, or the lander settling into soft soil. Subsequent analyses and improved image restorations have confirmed these features as artifacts, noise, or detached components rather than evidence of life. Yet despite rejection of the biological theory, the analysis revealed something unsettling. The surface of Venus was not a static painting, but a dynamic place where things moved, debris shifted, and the lander groaned and warped. The footage didn't show a dead world. It showed a violent interaction between machine and environment, with the impossible shapes likely representing dying convulsions of the probe itself captured in slow motion by the scanning camera. After 1982, Soviet priorities shifted as engineers realized landing in random spots provided excellent close-up data but couldn't map the entire planet. Venera 15 and Venera 16 launched in 1983 without landers, instead carrying massive synthetic aperture radar systems that mapped the northern hemisphere and revealed shield volcanoes, lava channels, and tectonic fractures. The data was scientifically invaluable but abstract, a topographic map rather than photographs. The final Soviet missions, Vega 1 and Vega 2, launched in 1985 as hybrid missions designed to intercept Halley's Comet, dropping landing units at Venus along the way that focused on soil chemistry and atmospheric analysis, while also deploying balloons that floated in the upper atmosphere measuring wind speeds. These landers didn't carry cameras because engineers decided imaging system weight was better spent on other instruments. With the collapse of the Soviet Union, the program ended. Original data from Venera missions was stored on magnetic tapes that began degrading over time, and with images appearing in newspapers and scientific journals during the 1970s and 80s, often grainy and low contrast as analog reconstructions of digital signals. In the 2000s, a new generation of researchers began digital archaeology, going back to raw telemetry data that modern computers could process much more effectively than 1980s mainframes. They filled in missing pixels and corrected geometric distortion caused by panoramic mirrors, revealing details invisible for decades, including soil texture, bedrock layering, and horizon lines further away than previously thought. Today, these restored images remain the only direct ground-level optical photographs ever taken of the Venusian surface. Subsequent missions have added valuable perspectives. Orbital radar missions mapped the planet, and the Parker Solar Probe's near-infrared detections sensed faint thermal emission from the surface through atmospheric windows in visible light during flybys. But no mission since has returned new photographs captured from the surface itself. Every other image of Venus you see is either a radar map, an artistic rendering, or a photo of cloud tops. We've sent rovers to Mars streaming high-definition video daily. We've flown past Pluto and captured stunning images of distant moons, yet for the planet closest to Earth, our visual understanding is frozen in 1982. We rely on data collected by titanium spheres that melted 4 decades ago. Until a new lander survives the descent, the yellow rocky plains of the Venera panoramas remain our only true view of hell. And the questions those images raised about what might be happening on that orange alien surface continue to haunt planetary scientists who wonder what secrets Venus is still hiding beneath those impenetrable clouds.